This is chapter 15, part 2. The equilibrium constant, we also call that K. So anytime you hear me say K, that's what I'm referring to, is a way to quantify the relative concentrations of the reactants and products at equilibrium. So when a chemical equilibrium reaction comes to equilibrium, remember, there's still reactant left and there's still product left. And since each chemical reaction that experiences this stops at a different stopping point, the K kind of tells us where it stops. And so remember that when equilibrium is reached, the forward reaction rate and the reverse reaction rate is the same. And because the reaction rates are the same, the concentrations of the reactants and products no longer change. We don't go to zero amount of reactant like we would if you had a chemical reaction like this. With this chemical reaction, because of the way that it's written, it's saying that all of this that we have turn into this. So one of the reactants runs out, the limiting reagent calculation. With equilibrium, that doesn't happen. We have a certain amount of reactant left at equilibrium, and we have a certain amount of product left. And that number is not changing, even though the reaction is still going forward and still going in reverse. And so constancy of the concentrations of reactants and products at equilibrium does not imply that the concentrations of reactants and products are equal to one another. So some reactions that reach equilibrium make tons of product. So we have way more product than we have reactant. Other reactions reach equilibrium when barely any product is made. So we have a ton of reactant left. So it all depends on that particular chemical reaction, and really it's also dependent on the temperature, but that's not something that we're going to get into. The amounts of reactants and products depend on the reaction and can be expressed numerically by the equilibrium constant K. So we're going to look and see how to calculate that. So when we calculate K, this is just a generic chemical equation where you have A plus B goes to C plus D, and then the lowercase letters are the coefficients. And the equilibrium constant can be calculated if we take the equilibrium concentrations of the product, C and D. So these are equilibrium concentrations. They can't be any time during the reaction. They have to be at equilibrium. And we plug those in for C and D. And then we do the same thing for A and B. And we raise the concentration of C to its coefficient. We raise the concentration of D to its coefficient, and so on and so forth. And so this is what we call the equilibrium expression. And just for further information, we're not going to get into the calculations today, but the equilibrium expression is actually unitless, and we're not going to talk about why. You're just going to have to take my word for it. And if you Google it, you will find that there's some controversy around that. But I believe that the K is unitless, and so do most textbooks. So here's an example. If I have this reaction where we have two N2O5s making two NO2s and one O2, we would take the concentration of NO2 and raise it to the fourth power, because 4 is its coefficient, and then we would take the concentration of O2 and raise it to the first power, because there's only one there, and then we would divide that by the concentration of the reactant N2O5 raised to the second power, because 2 is its coefficient. And so notice that the coefficients in the chemical equation become exponents in the equilibrium expression. So don't forget PEMDAS at this point. You're going to have to calculate this before you multiply by this, and you're going to have to calculate that before you can divide by it. So if we're going to write the equilibrium expression for the chemical equation, I would have K is equal to HF squared divided by H2 times F2, and it really is that simple. Now, heterogeneous equilibrium, hetero means different, so heterogeneous equilibrium means that we've got something in the reaction that is not in the same phase. So here, if it has a solid or liquid in it, then we don't include that in the equilibrium expression, and let me explain why. When we have these brackets mean concentration. And concentration means how many moles of a substance is dissolved in a liter, or how many moles of a substance are in a given amount of space. If you have a solid and you're saying this is pure carbon, then all of the space is occupied by carbon, and therefore it doesn't technically have a concentration. We're not saying that we're using a carbon rock that has other stuff in it. We're saying this is pure carbon. So therefore it wouldn't have a concentration, and it would not affect the equilibrium position of the reaction. Not that it wouldn't be made. It would still be made in this reaction. We just don't include it in K. So anytime there is a solid or anytime there is a liquid, you're going to avoid putting those in there. The only substances that are included in equilibrium expressions are gases and aqueous substances, because those have molarities that we can use in the calculation. So these are included in the equilibrium expressions. And those are the only ones. So when we look at this reaction here, we would say, okay, I'm not going to include this. It's in the chemical reaction, but I'm not including it in K. And I've got CO2 raised to the first power divided by the reactants CO squared. And then that's all you would have to do. So here's two examples. For A, I look at my stuff. I've got a gas here. I've got a solid, so I'm not going to include that. I've got a solid, so I'm not going to include that. So my K here would simply be the concentration of CO2. And then for B, I've got a gas, so that's good. I have a liquid there, and I don't include liquids. I have a gas and a gas. So my K is going to be equal to chlorine squared divided by O2 times HCl to the fourth. And so those would be my equilibrium expressions for the reactions.